Now let us understand the buoyancy force. How did you find the buoyancy force when you were high school students? So you calculate the buoyancy force to be the weight of displaced volume. Now that is what Archimedes had said to you. However, let us try to prove it. Consider a cube of water, delta x, delta y, delta z dimensions, and let us mark the forces acting on the top and bottom surface. Why we are not worrying about the surfaces which are facing the horizontal directions? These forces will cancel out each other. So we are only looking at the vertical direction. Now the top surface is under the pressure. That pressure force is F1, which is equal to rho gh delta x delta z, that is the area, if this surface is underneath the liquid column of H. Similarly, we can find the pressure force acting on the bottom surface is to be rho g. Now the height is h plus delta y, the area is delta x delta z. Let us consider the balance of these two forces. Now it is going to be upward rho g delta x delta y and delta z. What is this delta x delta y delta z? It is the volume of the cube. Therefore the upward pressure force is rho g volume, that is equal to the buoyancy force. Therefore we can conclude that the buoyancy force is also a pressure force. Please try these examples. Now let us move to another stage. That is the level rule and its applications. Now what do we mean by level rule? We simply say a pressure at 2 points at the same level are equal. However, we have to look 3 conditions and satisfy them in applying the level rule. The first is same level. Okay, we are considering only the same horizontal level. The second one is it is same liquid. So 2 points at same horizontal level which are the same liquid. Third is the connectivity. Now these 2 points have to be connected each other through the same liquid. If we are satisfying these 3 conditions, we can apply the level rule, or we can say the pressure at these 2 points are equal. Now how do we mathematically express this level rule? It is the variation of pressure with respect to the horizontal axis R0. Dabba P over dabba X is equal to 0 and dabba P over dabba Y is equal to 0, where X and Y are the 2-dimensional plane coordinates. Now with that, let us try to summarize what we have done. So far, we have looked at 2 specific cases in finding the hydrostatic pressure. The first one is the vertical variation, that is P is equal to rho g h. The second one is the horizontal variation, that is P is equal to 0. In addition, the above equations stands when the density is a constant. What if the density is a variable with respect to the depth? Therefore, there is a necessity to obtain a generic equation. Let us consider an inclined cylinder of liquid column which is at rest. You can refer this figure. Mark all the forces acting on this cylinder and we'll consider the force balance for the equilibrium. We are not worrying about the forces acting on the curved surface of the cylinder. Why? They are going to be cancel each other. So we'll consider the force balance along the inclined plane. If we do the analysis as it is given here, we'll get a simple differential equation, that is dP over ds is equal to minus rho g cos theta. Now we can apply the two specific cases which we have done, theta is equal to 0 and theta is equal to 90, and see whether we are getting the same answers. Now the generic equation will be the first integration of this differential equation, that is integral dP is equal to minus integral rho g cos theta ds. Remember, the minus sign stands for the direction. We measured the distance in vertically upwards here, whereas earlier h was measured vertically downward. Now these figures tell us the variation of pressure in the atmosphere and so on. You can use the level rule and the pressure variation with respect to the vertical axis in solving these simple manometers. Now when you have a simple manometer, you only have to look at the level rule and the pressure variation with respect to the vertical columns. Please try these examples. Now this is a special case where we have the inverted manometer. There is a particular reason to have the different geometrical view of the manometers. Please again search for them.